All right. Good morning, everyone. Only 3 more classes left. So a few logistics up. There's always updates. The big question I get is, when is the response get graded? The answer is similar to test 1. Specifically, they'll be graded 2 weeks from when test 1 was done. 2 weeks from when test 2 was done. So that means the deadline I gave the graders was this Thursday. This Thursday was when they will be done grading. Now, I then have to actually look at them and actually, do some things and actually, I have to standardize the grading so that one grader wasn't more unfair than anyone else or whatever. So all that to say, Friday is the goal. I'm going to check with the graders this week, hear how things are going. I myself graded a subset of the tests. I graded about 35 to 40 of them. And the reason I do that is so that their grades, when I get their grades, I make their distribution look like my distribution. I kind of set the standard for grading. But that's why it's not just they don't just put the grades in whatever they grade. I make sure that the grading is equitable. That's why it takes a little bit more time. All right. The solutions are posted, so that's what I have here. Just like the test 1 solutions are posted right after the exam, the test 2 solutions are posted right after the exam. Where do you find them? In the test 2 folder, in their fall 25, 2049 test 2 lecture answer. That's what it looks like in my file thing. So this is here. It's a PDF. I'm not going to really talk about any of the multiple choice because there wasn't really any predominant ones that were missed. Oh, sorry. Okay. I will post the ones with these worked out. I somehow don't have that. So I didn't realize that the ones I posted. I'll post the ones with the worked out solutions here. In fact, let me just open them for you so you can see them, just to show you that I am going to do that. But I want to point out one of them that was a struggle, and it was one that I was surprised with. This one actually went fairly smoothly. Basically, if you messed up this question, it's because you treated the left one like an infinite wire. That was the most common mistake that people made. So it's finding an infinite field due to this situation. You break it into 3 pieces. Wire 1 is semi-finite, semi-infinite arc, and then a straight one. This one does nothing. This is just a half loop. And this was a semi-infinite. You actually had to use that. Great. This one was the one that I probably saw the most mistakes on. This one, I guess, is wrong. You really want to make sure you do series in parallel. I saw a lot of mistakes with series in parallel. So to clarify, and I'll just kind of go through each of these. So for example, these 2 here are in series. Why are they in series? Because they're one after the other with no junction between them. These 2 are in series. So these are in series, these are in series. Then after you combine them, those are in parallel. And y'all can kind of see, I'll post the solutions with these, and you can see what I do is every time I combine them, I draw a new picture. I saw a lot of people try to call these in parallel. They are not in parallel. Why? They share a junction at the beginning, but they don't share the same junction at the end. There's a bunch of resistors and junk in the way. These are not in parallel. These ones on the corner here, these are not in parallel. This entire branch is in parallel with this entire branch. The beginnings and the ends of the entire branches. So there will be a question on the final about, hey, here's a bunch of resistors, combine it. There'll be a question on the final that says, hey, here's a bunch of capacitors, combine it. Can you do series in parallel? It'll be a couple questions out of the 40. This one largely went smooth, though I was a little, to put it, it's a little disappointed in the calculus. The mistakes I most often saw here were mistakes that you all shouldn't be making. A lot of people, specifically this integral here, the 1 over y plus 1's the third, a lot of people made mistakes in the integral. Now, you don't lose a ton of points in this exam with that, but I do really want to stress you need to be able to, every single integral up here, I would call a trivial integral. I would call these are all Calc 1 integrals, and you all need to be able to do these integrals because your future classes are going to have integrals. Just like you all need to be good at algebra, you need to be good at least at Calc 1 integrals, Calc 1 derivatives, things like that. obviously more than that, but this is the base. This is like the easiest integrals get, roughly. This one on the left, this one in the middle is kind of maybe the easiest, but they're all, in my opinion, on the same level. And this one in particular was a struggle. All right. This one, if people knew how to do it, it went smoothly. If people didn't know how to do it, it didn't. This is one of those situations. Rotation, you had to realize, we did a few rotation problems. If you did it, you would kind of recognize it. If you haven't done it, you won't. The key part here is that I asked for the amplitude, which was just this term in the front. And I asked for the amplitude of current, so you had to divide it by resistance. Voltage divided by resistance is current. And that was it. This fifth problem was the one that the studio class got. They get an extra problem that they have to do. So there you go. I'll post these all worked out. Apologies for the ones I posted not just yet, but I will post these. Last two things of note. This Friday and Monday I'm going to be out of town, so the really only big impact is I'm not going to have office hours on Monday. In return, I'll have office hours this Thursday, so I'll send out an announcement about that. I'll have office hours this Thursday, 12:30 to 1:30, to accommodate me not having office hours on Monday. I will straight up tell you, there's just not enough day, regardless of that, there's only 3 days. So again, I'm going to get the exams this Thursday, Friday. There's only Monday and Tuesday and then Monday, and then it's our final as far as weekdays. So realistically, it's not going to really be feasible to come and review your test 2 for your response. You can. The Monday of the final exam week, I will have office hours. I will make them a couple hours. Yeah, I'll do a couple hours that Monday. And next Tuesday, I will have office hours. So it is possible to come to review your final exam, your free response. However, honestly, with these solutions, this should honestly be fairly sufficient for you to identify how to do these problems, look them over, try them, all that kind of jazz. For studying purposes, this should be sufficient. But of course, you can come on those couple of days to review.
Okay, what day specifically is our final?
Your final is December 2nd from 10 to 12:50 in this room. Reminder, this is a good reminder for you for all your classes. So I did post that and everything. But in case you're curious of any classes, all your professors will appreciate if you know this. If you just Google UCF final exams, this is something you may not know exists. This is how I find when your exams are. This is how, they don't send me an email. This website, you just pick your class pattern, you pick your start and end time. And so this is a super useful thing for all of you to know for your future UCF career. So if we just put in our class here, there's our exam. So this is true of every UCF class you take. It does not tell you where the exam will be, but ours will be in this room. Okay, I think that covers everything. Reminder to y'all, studying-wise, I'm not going to make some big fancy review for the final. Why? Because I've already made a bunch of big fancy reviews. If you want to review stuff from Test 1, go to the Test 1 review. If you want to review stuff from Test 2, go to the Test 2 review. For the last stuff I'm covering, I will make a 5 or 6 PowerPoint slide, but it'll be hopefully fresh in your brain.
Can you just reiterate the format of this final?
The format of the final currently will be 40 multiple choice questions. It will be 40 multiple choice questions. Now, previously, these multiple choice questions will include questions that are in the order of difficulty as the free response. Not quite as involved as the free response on previous exams, but because there's no free response, it doesn't mean I chop off the high difficulty problems. It just means they get incorporated into the multiple choice. There will be 40 multiple choice. My goal when I make this test is that I can finish this test in about 25 to 30 minutes. If I can finish the test in 25 to 30 minutes with writing stuff out, actually writing out the work that I would do to solve the problems, not just doing it in my head and doing stuff like that, then that means that basically you have 5 times as much time as it takes me, so that's kind of how I gauge this things.
So you get the whole time?
You get the entire 2 hours and 50 minutes. Now, I will warn you all, it will be a very hard cutoff at that 2 hours and 50 minutes because my next exam is 10 minutes after that. So I have to go upstairs at 1 o'clock to give their exam. that day. So we will not be able to sit around and dilly-daddle after that. But I will design the test to be very doable within that 2 hours and 50 minutes. In my opinion, you will have more time on this test per problem than any other test that I've given you thus far. Time should not be a concern, unless you don't know what you're doing.
How many classes do we get?
40. 40 split across every topic based on the amount of time we covered that topic. Yep. That's the current plan. Things could change, but that's my current. That gives me, we have roughly 10 weeks. That gives me about 4 problems per week. If I start to do less than that, it gets a little tricky to cover everything. And it will be a mixture of trivial problems, and it will be a mixture of problems that take a little bit of time and in between. So, all right.
You get the note card, right?
You get the 5x8 note card. I'll start bringing those this Thursday. Yep, this Thursday I'll bring the 5x8 note card. You get one 5x8 note card, just one.
Both sides of it?
Both sides. Yep. Okay, so last class I started teaching you all about waves. And I'm just going to kind of jump down to the wave equation because that was the main thing at the end. All of this was just to get to the derivation, was just to derive the wave function. This is any wave, anything that's periodic and is quote-unquote moving is described by this function. There's lots of different types of waves out there. Sound waves, mechanical waves. Sound wave is a mechanical wave, but like wiggling the string, water waves. What we're going to learn now that I've given you a background on what a wave is and the equation for it, is we've said that light is a wave. And so now we're going to take this exact equation and just make it for light. Now, before I kind of do that, okay, let's see if these, let's just give you all this question. This will be a good review. See if you remember it. I'll give you a couple minutes on this because it's going to take a bit. Here are 2 waves. One wave is given by A, I'll replace A with a number, not that it matters at all for this problem. Let's just make them have the same value in the beginning. 0.2 times sine of 2 pi over 2x plus 2 pi over 2t. The second wave is given by 0.2 times sine of 2 pi over 2x minus 2 pi over 4t. How do their velocities compare? The first step you should do for this problem is to actually write down the wave equation that you're going to compare to. What is the template for the wave equation? What do I mean by that? Make sure you write those down somewhere on your paper. That's what you're going to be comparing to. Half of problem set 3 is, can you read this equation? Can you make sense of it? Can you apply it? 30 more seconds. All right, and 5, 4, 3, 2, 1. All right, so this is the wave equation that is given on your formula sheet. I did, to make it easier for you. Yeah. All right, so this is the wave equation. Now, make this look like the other one. How are we going to do that? Transfer in that 2 pi over lambda. So we get 2 pi over lambda times x minus plus 2 pi over lambda times v times t plus the phase shift. We're not going to actually, I keep mentioning this phase shift. We're not actually going to worry about it too much. Okay, so looking at this equation, in front of the x is the term 2 pi over lambda. So 2 pi over lambda is this thing in front of the x, and it's the same value. In front of the t is not just v, it's 2 pi over lambda times v. So with that in mind, this whole thing here, 2 pi over lambda v, equals 2 pi over 2. Why do I say that? So therefore, 2 pi over lambda times v times t, actually I don't need to write that, equals 2 pi over 2. Why? Because you can see they equal each other. Oh, that blue is not great. Let me pick a different blue. The contrast is always fun. Yeah, that's good. All right. These two things are equal to each other, so I set them equal to each other. So you can solve for V1. This should be a trivial math problem. Oh, there is one thing I missed here, though, when I wrote this down. This minus plus sign means I need to flip the sign. The minus plus sign means I need to flip the sign. Reminder to you all that when you add, that means I'm moving to the left. When I subtract, I'm moving to the right. If you ask, why is that? We spent a bunch of time on that last time. It's a good question, but one you'll have to kind of look through. So great, this all cancels, this all cancels. So what does V1 equal? -1. When they cancel, it doesn't equal 0.
I thought that was 2 pi over 2.
You're right. It still cancels. What is lambda? Yeah. Yep. It's 2 because, and that's, I made this easier for y'all. All right, so the same thing on the other side. If I now color code those ones for you all, this means 2 pi over 4 also equals that green thing. So 2 pi over 4, 2 pi over lambda equals, let's go ahead and actually put what lambda is, equals 2 pi over 2 V2 equals 2 pi over 4. That means V2 equals 1/2. V2 is half the velocity of V1. Specifically, it's -1/2 the velocity. So if I want to write this in terms of V1, V1 is not half of V2. It's not smaller. It is bigger. This always throws people off. A lot of people look at this and say, wait, but this is 1/2. Why wasn't this 1/2? Think through the logic. If I put 1/2 where V2 is, what's 1/2 times 2? It's 1. V1, this statement says that V1 is 2 times V2. It is twice as big. Check our numbers. V1 is twice as big. People get thrown off by this all the time. Make sure you're reading these as sentences. Yeah.
How do we know to make them equal to each other?
So I didn't set them equal to each other. Like for this step here, like how do I get the answer? Or like how did I do this bottom part?
Well, because you have the 2 pi over, across the,
I matched them to the equation up there. Yellow equals yellow, green equals green. Yeah.
Is the green term in the original? Is the green term all these? I guess the same thing as omega.
Yes. Yeah. The question was: is the green term always omega? Yes. There is another thing you can do here. Is when you have this form, the velocity equals the second term, or sorry, the first term divided by the second term. You can kind of see that if you set this up. There is a thing that says that v equals k over omega. Let me check my units there. Nope. Omega over k. V equals omega over k. That's another thing. It's not in the form of the sheet, but you can derive it there. All right. Cool. Okay. Now, great. Waves. We're done with waves. That's waves. Now I just need to put it in the context of electric fields and magnetic fields.
Sorry, why was the first one negative again?
Yeah, it's negative. Good question, because there's a plus sign here. This minus plus tells us we need to flip it. Yep. Okay. Light is a wave. This is proven theoretically. This is also proven experimentally. So if you all remember way back in the beginning, I showed you a really cool simulation and I said we're going to keep using it. Where is that simulation? So this simulation, fantastic thing to fiddle around with, a lot of fun. This is what a wave looks like, and again, I showed you can do a 3D view, and yay. This is what waves do. And I showed you all that, like when you had a wall, that light goes around the wall, or that waves go around walls. What also goes around walls? Light does. Light goes around walls. And you're like, what do you mean it goes around walls? If you all have your door cracked a tiny bit, it fills the whole room. You can see in the entire room. Why? Because it's a wave, and it spreads out. Light does not act like a laser beam. Now, then the question is, how the heck do lasers work? And that's a more complicated question. Light does not always act, pretty much never acts like a laser unless you make it a laser. There is also something called the double slit experiment. That's a classic, where you get these two slits and you get this effect. You get this with water, you also get this with light. And you get this thing called an interference pattern. If I kind of looked at the end here, you get these places that are big wiggles, and then you get these areas that are like no wiggles. This is a classic physics experiment, this double slit experiment. Whatever. Light's a wave, experimentally proven. Very simple. Light is also a wave, proven theoretically. There is something called Maxwell's equations, and I've kind of taught you Maxwell's equations. Maxwell's equations are the 4 equations that explain all electricity and magnetism. And if we look at the names of them, you can see that you're going to recognize, hopefully most of them. Gauss's law is one of the equations. Gauss's law for magnetism we haven't really looked at, but it's a fairly trivial one. It just kind of looks like this when it equals 0. Faraday's law, you've seen Faraday's law. Ampere's law, you've seen Ampere's law. Now notice this was called Ampere-Max law because he added to it. It was missing something he added to it. We're not going to worry what he added. But all that to say, if you use these equations and you kind of set up this problem, we're not going to go through it because it's really complicated. You end up with this. You end up with this expression that the second derivative of the electric field with respect to time equals a constant times the second derivative of the electric field with respect to time. Sorry, electric field with respect to distance equals the second derivative with respect to time. And you may be like, why does this matter? If we go way back to the beginning of this PowerPoint, this is the wave equation that I showed you all. If you compare the two, you know, if I just copy this thing and I paste it next to the other one, they should look pretty darn similar. They look pretty much the same. So the solution, if the solution for this one was a certain solution, it's going to be the exact same solution for that one. So this is theoretically how it's proven. Now, again, everything's based on experiments. This thing we'll reference at some point. This just says there's a relationship between E and B, that they're perpendicular to each other. Okay. Now, I want to do something I think that's pretty cool exercise. So, there's the two equations. There's the general wave equation. There's the one for electric fields. Remember, they look pretty darn similar. Solve for V in terms of epsilon naught and mu naught. If you're like, how do I do that? Just look where V is here. Look where the other stuff is here. See, I think you all can kind of put the pieces together. Solve it, and then if you solve it really quickly, if you find the answer, you can check your work. If you're like, what do you mean check my work? Plug in the numbers.
Are those the same epsilon and mu naught and mu?
They are. These are the exact same. So epsilon naught is 8.854 times 10 to the minus 12. Mu naught is 4 pi times 10 to the minus 7. Whatever answer you get, I want you to check your work. How are you going to check your work? Plug those values in and see what it spits out in your calculator. It's a cool result. You'll know when you see it. Hopefully. This is a number that we had mentioned in this PowerPoint, but you've also probably learned in a previous class, middle school, high school. May or may not. Most of you have. But it's a really cool result that comes from this. It proves that these equations are accurate. What you're solving here is the velocity of an electromagnetic wave. That's what we're deriving here, the velocity of an electromagnetic wave. Alright, I'll give you all about 30 more seconds to get the answer, but I do really want you to plug it in your calculator because that's cool. All right, in 5, 4, 3, 2, 1. All right, so hopefully you realized that this and this equal each other. Why? Because, just compare the two equations. They look pretty darn similar. So epsilon naught mu naught equals 1 over v squared. So therefore, V equals 1 over the square root of epsilon naught mu naught. That's our answer. Now, I told you to prove this. So plug in the numbers. When you plug in the square root of 8.854 e to the minus 12 times 4 pi e to the minus 7. These are numbers that you're like, these are gross. How is this going to get me anything of significance? When you plug this in, you will get 2.99 times 10 to the 8 meters per second. If I round that number, if you don't see it yet, maybe once I round it, this is the speed of light. So this is a really cool thing that comes from, if you measure epsilon naught and mu naught really accurately, you can calculate the speed of light you can determine what it is. It is much easier to measure epsilon naught and mu naught. How are you going to measure the speed of light? It's not like you can flip a light switch, get a ruler out and a stopwatch and do that. It's not an easy experiment to do. They could not do this 50, 60, 70, 80 years ago, but they could measure epsilon naught and mu naught really accurately. And fun fact, all units now, this is something that they've done, all units are now defined in terms of the speed of light. So the kilogram used to be the base unit. They had literally a solid sphere of titanium or something. I forget what the material was. And everything was based on this kilogram of titanium. The problem is it loses atoms periodically, so its mass changes over time. The speed of light in the universe is a set thing that, as far as we understand, does not change. And so they define a meter by the distance that light travels in 1 second. 1 second is also quite easy for us to quantify. 1 second is defined as, I don't know the number. It's like a crazy number of oscillations of a certain atom. These cesium atom, it's a crazy number. When a cesium atom vibrates a bajillion times, they have a specific number, that's 1 second. They can literally count how many times it vibrates, and that's 1 second. And that is set as well.
So, we were to substitute one way in the other, we're just using that they were very small.
Yep. All right, so great. Speed of light. It's cool. This is the speed limit of the universe. And this is a very important idea that you've probably maybe heard before, that nothing goes faster than the speed of light. If it exists, it exists. But as far as I understand it, and something I want to stress here, when I say this is the speed limit of the universe, I'm not thinking of rockets. I'm not thinking of particles. I'm not thinking of that. I'm thinking of information. That is the key here. This is the fastest that you can transmit information. This means that it is impossible, okay, for the example I'd like to give, it takes light 6 minutes to get from the sun to us. 6 or 8, I always forget. 8 minutes. 8 minutes to get from the sun to us. What does that mean? It means if the sun blew up right now, you would not know for 8 minutes. If the sun blew up right now, you would have no idea. 8 minutes later, you find out. That is the fastest that information can travel. Meaning, if you try to communicate with a spaceship on the other side of the solar system, it takes time. Hours, potentially, depending on where the thing is located. Meaning, if you want to control some spacecraft that's going to land on Mars, you are going to have potentially 30 minutes to an hour delay. You tell that rover to move to the right, great. An hour from now, it's going to move. Because that's how long it takes. Now, what is being transmitted? What information is being transmitted? This electric field. This oscillating electric and magnetic field. That is the information, and we can encode information in it by making it wiggle faster, making it wiggle slower, things like that.
So it takes so long, like what happens if like there's an emergency like a spacecraft?
Sucks to suck.
Okay.
Yeah, the question was, what happens if there's an emergency in a spacecraft? This is why humans are useful to have on board. The closer a human is, the faster they can respond to it. If you have really good programming, you hope it responds well. But yeah, when they land on Mars, when they have these things land, it all has to be autonomous because humans can't control it. Things change too rapidly. If you in the camera notice that you're about to hit a rock, you already hit the rock. You hit the rock 30 minutes ago.
This is kind of off topic, but didn't Neil deGrasse Tyson say once you reach like the speed of light, time stops?
Yeah, so there's some weird stuff. If you don't take physics 3, there's something called special relativity. And as you approach the speed of light, all sorts of weird things happen. Your length contracts. So someone could measure you with a ruler, you measure smaller. If someone saw you on a spaceship and you were traveling close to the speed of light, they would see a clock moving very slowly. You would see the clock moving normally, but someone else would see it moving slowly. So if you all watch the movie Interstellar, that happens when they get close to really strong gravity. It also happens when you approach the speed. Weird things start happening here. The other thing that also happens that's significant is your mass. Your perceived mass increases, which means it's harder to get an acceleration. F equals ma. If your mass goes up for the same force, you get less acceleration. So that's why it's impossible for us to reach the speed of light, because your mass gets infinitely large, and so you can no longer accelerate. That's true for everything. Everything here, yeah. So, this is a really profound kind of idea, the speed of light thing, and it's the fastest information can travel. One of the reasons so I guess I'll show you the equations real quick. This is going to look intimidating. It's the same equations that we just did. We replaced amplitude with E. We replaced amplitude with B. We replaced velocity with C. It's the exact same equation that we saw before. Y equals x comma t equals the amplitude of 2 pi over lambda times x minus plus vt. It's the exact same equation. All we needed to do is replace the amplitude with what is making the amplitude. It's the electric field's amplitude. Or in the case of B, it's the magnetic field's amplitude. We replace V with C. Why? Because that's how fast it's going. All light travels at C. With a caveat that also has a caveat. Light, quote unquote, slows down when it goes to materials, but it doesn't actually slow down when it goes to materials. Yeah, we'll talk about that when we get to that. Another thing is I tell you all that things, that light always travels at sea. Those are really crazy. So like, you may accept this, but then I'm about to give you situations that make me doubt this. Say I'm on a spaceship traveling half the speed of light and I shine a flashlight. Do the speeds add? No. That light is also still traveling the speed of light, and it's a really weird thing. You add velocities, they don't just add when you're going really fast. You have to do different math. That's where special relativity, general relativity. A lot of the physics I'm teaching you all, this was known for a few hundred years. In the past 100 years, the new physics has been quantum mechanics, special and general relativity, some other fields, but those are kind of the big buzzy ones. If you want to learn about those, Physics 3 is where they cover some of those things in a very simple way.
So, like, the light year is like traveling 1 year at the speed of light.
It's the distance light travels in 1 year. Okay, so great, there's these. Now, something I want to talk about is where do these come from? You know, how do you make these waves? It's the same way we make every wave. You know, if you want to make a string, I have a pretend string, I want to make it wave. What do I do to the string? You know, you wiggle it, you make it vibrate up and down. If I want to make a sound wave, what are my vocal cords doing? Vibrating. What are we going to vibrate to make an electric field vibrate, to make a magnetic field vibrate? What's the thing that we've been talking about this entire class? What's the thing that makes these fields / experiences these fields? Charges. So I'm actually going to jump down a bunch of slides because before we get into the math, I just want to motivate how we make these waves and how you receive these waves is going to help us maybe understand this in not just a math sense. So I got a couple of simulations here. I'm going to actually reference the second one. The first one is cool. We'll look at both of them real quick. So, charges make fields. We've talked about that. A charge makes an electric field everywhere. A moving charge makes a magnetic field everywhere. These are things we've talked about. This is not new information. What is new, if I move this charge down, the field way over here doesn't know it's moved yet. This field does not update instantaneously. It takes time. How much time does it take? Remember I told you all the speed of light is the fastest information can travel. What is the information? The information is that the field will change. So when I talk about an electromagnetic wave, what we are effectively seeing is the electric field where the charge used to be, due to the charge where it used to be. That's the idea here. So I'm going to start to kind of oscillate this thing, and we're going to get this field, and I'm actually going to pause it. So right now, if you'll remember, let's just get this a proton just to make things easier. We don't actually oscillate protons, but just to make our life a little easier. Notice here the field points down. Why? Because electric fields point away from positive charges. That's not new information. It points down here because the electric field points away from positive charges. Now, over here, it should also be pointing down. Why isn't it pointing? Because look, this point is below this. You know, it should be pointing like down to the right or something like that. Why is it pointing up then? This doesn't know that this charge is up here yet. It hasn't, quote unquote, seen that it's up there yet. So what you are going to notice is as this wave moves, basically these points in space will be like, oh, it's up here. It's seeing it in the past. This is kind of a crazy idea, but this is what I really want to convey to you all when it comes to this stuff. When you look at the sun, which obviously don't stare at the sun, you are seeing the sun 8 minutes ago. You are not seeing the sun right now. You are seeing the sun 8 minutes ago. So one of the things they make the claims of in astronomy, and this is accurate, this is something that you might have heard, when you're looking at stars, you're looking backwards in time. You are not looking at the star right now. You're looking at the star, however long it took that light to travel, that's how far in the past you're looking at it. So the bigger and the better telescopes they build, they say, quote unquote, the farther back in time we can look. And that is true. The farther we can see in the universe, the older that light is that is reaching us. So, when it comes to this stuff, that's why you get a wave. It doesn't update instantaneously. The field everywhere doesn't update instantaneously. It's not just pointing down because this thing's moving, and this is exaggerated. This is so quick that you all can't actually see this. This oscillation is much quicker. Now, as this wave travels, as this information travels, I have another particle over here. I have an antenna filled with charges. What happens to a charge in an electric field? It moves. It experiences a force. Why is this useful? I'm going to make this charge start to wiggle. The electric field will make it start to wiggle. That's how antennas work. All an antenna does is it's a rod that when a field hits it, the charges wiggle. Why? Because of what we learned in the first test. Electric fields make things. So look at that. It starts, and now granted this one's getting pushed the opposite way because we're going to call it an electron, which I don't know why they did opposites here, but whatever, don't worry about it. This one's moving the opposite way because we're going to call it an electron. Electrons move opposite to the field. All right, and there's
The one on the left is oscillating.
There we go. So this one's, I don't know why they show the fields opposite. It's kind of weird, but it's fine. So you all can play around with this. This is what the field, this wave does not just spread out in one direction. This field spreads out radially in all directions unless you have some way to direct it. There is ways to direct electric fields. Satellite dishes both can collect and send it out in one direction. But these big towers just transmit everywhere.
So the left one is just oscillating on its own, right?
Yeah, there's a current. So this is let's call it a radio station. They are transmitting at a specific frequency. They are driving a current at that frequency. And in turn, they make a wave with the exact same frequency.
So somebody was trying to transition, like receiving that.
Yeah! You can listen to any signal out there you want.
They just hear like a certain person.
Yeah, they won't hear it now. The problem is, the question was if someone wanted to listen in on this, what are they going to hear? I'm showing you one source here. The real world has crazy amount of sources. Every single one of you has a cell phone. If you're all on a phone call, that signal is being generated, and every single one of your phones is getting the same. You are in a soup of fields right now. You have to tune to the frequency you want. How do you tune to it? That's where circuitry gets involved, bandpass filters, things like that. You got to select it, and it even gets more complicated than that. Yeah, there's a lot of really cool stuff here, but there you go. The other quick simulation I want to show you all, that was a radio tower. That was like the simplest case. This one here is the same thing, but it's a little bit different showing it. This is a current that's oscillating up and down and making a field. One of the ones I want to kind of show that I think is a little bit more interesting. I mean, they're both interesting. Now, isn't it? I'm going to show you all the current loop. And I'm going to slow it down because this is way too fast. Yeah. And then I'll increase the brightness. This is a loop of current. As the current oscillates, the charges move in the thing, and as they move, it's making an electric field and a magnetic field at the same time. Currently, you're seeing both, but if you just want to see one of them, there's the electric field oscillating outwards in space. If you want to see the magnetic field, I'm sure that's somewhere here. You can see dB/dt. Anyway, fun things to kind of play around with. But yeah. Antennas take all different shapes and forms, but they oscillate current. As that charge moves, it makes an electric field that moves. As it also moves, you all know that a current carrying loop makes a magnetic field. As that current varies with time, so does the field it generates.
So nothing was moving, but there's still be just an electric field.
Yeah, it's a great question. If nothing was moving, you wouldn't get a wave anymore. You would just get a constant electric field that would just decrease.
No magnetic field, right?
No magnetic field, correct. Yeah, to make a magnetic field, you need a changing electric field. They're coupled. All right, so I just wanted to show you all of these to motivate why we're doing this and how these waves form. You don't need. I'm not going to test you on any of this, but it's the actual practical application of this. All right, so we found the speed of light. Here are the wave functions. Yay! This next one again, it's going to look intimidating. But let's just kind of read this before we get overwhelmed. B and Z, there's the equation for the magnetic field. Notice it's in the Z direction. So the magnetic field is going to oscillate. Let's say Z is left and right. Maybe like what? Don't worry about it. I'm just going to say it's left, right. The electric field is in the y direction. So the electric field oscillates up, down. The magnetic field oscillates left, right. But they're at the same time. They're perpendicular to each other. This is how these electromagnetic waves work. If I go back to the very first picture I showed you all in this entire thing, they are 90 degrees to each other. As the electric field goes up, the magnetic field goes up, but in a orthogonal direction. And they're in these 90 degrees directions, and this equation is the one that we're going to kind of look at to relate them. Great. Here's a function for B. Here is a function for E. Now, you all may or may not have seen partial derivatives before, but they're very simple. This function here says take the derivative of this left one with respect to time. Pretend like x is a constant. A partial derivative, you take the derivative with respect to the variable that says so. Everything else is a constant. On the right side, I say take the derivative of E with respect to x. Everything else is a constant. So, take the derivative of this left function with respect to time. Take the derivative of the right function with respect to x. Set them equal and see what happens. Try it out.
One's supposed to be in the z, one's supposed to be in the y direction.
Yeah, but it doesn't actually matter mathematically. Yep. Take the derivative of the sine function with respect to t. Take the derivative of this sine function with respect to x. Set them equal. Try it. You're going to need to write this down. This is not a do-in-your-head situation. When you set it equal, you're going to notice a lot of things cancel out. Not everything. Which one I pick? The one that is right? Because I made these. To be honest, though, I don't actually have it memorized. I know what the relationship is, so I'd actually derive this myself. I know which one it's between, which two, but I'd actually have to think about it more than just looking at this. I'd have to think like 20 more seconds. When you do the derivative for 0, yes. And you want to do the derivative correctly. Now, it ends up not mattering, but to do the derivative correctly, then yes. All right, gonna give y'all about 20 more seconds. All right, and 5, 4, 3, 2, 1. Okay. We're not going to really worry about the minus sign here. There will be a negative sign that gets calced out. We don't really care. All right, this first one, if I take the derivative of a sine function, the amplitude, we keep it. Sine turns to cosine. So we get cosine of 2 pi over lambda times x minus plus ct. Then we do the chain rule. You take the derivative of the inside. In front of the t is a c. Not only is there a c, there is also a 2 pi over lambda. If you want to make sure you're doing the derivative correctly, you better spit out that 2 pi over lambda. If you didn't, you just didn't do the derivative correctly.
Was the first one supposed to be with respect to x, or was the second one supposed to be with respect to?
The second one. You can see it up here.
Wait, then why are we
Because this 2 pi over lambda goes to both terms. It's outside of the
lambda on the outside of the cosine?
I just did chain rule. And I can put it in the front. It's multiplication. It doesn't matter. 2 times 3 is the same as 3 times 2. I happen to do the outside first. I did the outside first. I did the inside second. I multiplied. If it makes you feel more comfortable, I could put it there instead. It's the same thing.
Yeah, I'm just confused on why it's 2 pi c over lambda, because I have
Distribute it.
No, I did. I'm just not sure.
Derivative of the inside is just that term in front of the t that comes out. I'll let you kind of think about that. Yeah, the minus plus sign I'm gonna kind of hand wave away. Yeah. Technically, there's like it depends which way this wave moving depends on whether you get a plus or a minus. So I'm just not gonna worry about it. I'm gonna pick the plus. Oh no, but all right. So this is the left side. Again, this is a derivative that you all should be able to do. This is while it's technically a partial derivative, it's just a calc 1 derivative. All right, this right side is E naught. Again, cosine of 2 pi lambda x minus plus ct. This time we just spit out a 2 pi over lambda. Great, this cancels, this entire behemoth cancels, this 2 pi over lambda cancels, this entire behemoth cancels, this 2 pi over lambda cancels. So we get B naught times C equals E naught. And then you're careful and you realize all the answers are in terms of B naught, so you move it around.
I'm still really confused on why it's this way. I have it the other way around.
The first one's with respect to T. T's right there. I can answer more maybe after class. At this point, I'll have to look at what you did. All right. So, what's the? Yeah, go ahead. Yeah, what is B naught? This is the amplitude. We remember what these functions represent. That's a great question. What is B naught and E naught? E naught is the amplitude of my electric field wave. This field that's made by electric field, this wave made by electric fields, E naught is the amplitude, the maximum. It's the maximum amount how big that wave is. In fact, let me pull that picture. What is E naught? This is E naught, the maximum of that wave. What is B naught? The maximum of that wave. That is a great question. Is the maximum value that wave can possibly be? The amplitude. All right, so what is the consequence of this expression? The consequence of this expression is that the magnetic field is way smaller than the electric field. How do I know that? I'm taking a number and dividing it by 3 times 10 to the 8. That is 30 million. 300 million. It's quite large. Divide any number by 300 million and you're going to get a really small number. Magnetic fields are not easy to make. Strong magnetic fields are much harder to make than strong electric fields. Do the units work out? They do if you realize that certain units are related. But then I'd have to kind of get into that. It's a good question. Yeah, electric fields and magnetic fields are coupled. They are just different things. They're the same thing, but different. All right, so there's an updated slide on that showing that you can get C from a couple different ways. The magnetic field is always much smaller than the electric field. Now, the interesting consequence of this, and I need to double check this, I looked into it, and I think it's accurate, but I need to triple check it. When it comes to antennas, the electric field dominates. So the electric field, the antennas are the thing that you will pick up signals with. The electric field is the one going to make those charges wiggle. That's going to dominate the signal you receive. However, if you had a loop of wire, and that was your antenna, you can make an antenna with a loop of wire. If you'll remember, that oscillating magnetic field is going to make a current, Faraday's law. The magnetic field will oscillate for circular loops, antennas, and the electric field will dominate for straight antennas. Which one do you prefer? It depends on your application and purpose and yada yada.
Is there ever a time where antennas get overwhelmed by how many signals they're getting? Like even with all the technology built?
Yeah, it's a good question. Is there a time where antennas get overwhelmed? They will only get overwhelmed if one of the signals is very large. These signals spread out over space, so they weaken pretty quickly. But if you had a really strong signal, then it would induce a current in it that could be so strong you could break it. So, case in point, electromagnetic pulses, nuclear bomb, those make really strong electromagnetic waves that would fun fact, every single piece of wire acts like an antenna if you have a strong enough field.
Is there a way, I'm assuming there is a way to like track like, hey, here's a antenna, how long does it take for the signal to reach some other antenna?
Oh yeah, speed of light. Yeah, so that's a great question. Is there a way to track how long it takes for a signal to reach something? Take the distance divided by the speed of light, and that's the time. That's actually, that's a great question. That's a question we actually had at the very, very beginning. Before I even taught you about electromagnetic waves, I said how long does it take for a signal to reach you? It's literally just take the distance divided by the speed of light. Yeah, so light basically travels that speed and everything. Air, vacuum, all that jazz. All right. Yeah.
So why is it electromagnetic waves like light can travel from vacuum?
Yeah, why can light travel through a vacuum? Because these fields can exist anywhere. Every problem I've taught you all up to this point, I just said find the electric field there. There didn't need to be anything there for the field to be there. These fields are not like a real physical thing that travel through medium. They are just information that's traveling. It's kind of a crazy idea.
We're not in a vacuum, right?
No, vacuum means nothing, no air. Yeah, light requires nothing to travel because you're not transmitting through physical media. You're just transmitting this oscillating field. And the field then affects materials that are placed in it. So it's kind of a weird idea.
So if they got like weaker over a certain distance, how do they make like the plane towers to like be able to reach it?
Yeah, the question is if they dissipate over distance, how do you actually pick them up? Really big antennas, really, really sensitive equipment. So there's a reason we sent the Voyager spacecraft and it's outside the solar system at this point. That signal has gotten weaker and weaker and weaker and weaker, and at some point it becomes so weak that we can't pick it up anymore. But we have really good telescopes. A telescope is just a really big radio. If you increase your... That's a nice segue into this next one is the intensity, the energy carried by a wave. That's the next thing we're going to talk about.
Voyager is the one that has that distance thing.
Yeah. It's the farthest man-made object in the universe from us, because we literally sent it out of the solar system. All right, so let's see if this all made sense. Here's a wave. Now this wave is written in a slightly different... I'm just going to kind of remind you all of this, that this is our general form. Amplitude, and this one's a cosine wave. It doesn't really matter that it's a cosine wave. They're just shifted. You know what? I'll write this one this way. So I've given you all this, and so I'm just going to remind you very quickly. That this and this are the same thing. All right, so great. You didn't actually need to know that to solve this problem, but what's about a E-naught? I'm a little nervous I didn't put the right answer up there, but we're good. Yeah, right into your face.
So the only difference is that you add a angle.
So this is the full wave equation. For this one, we're solving for the amplitude of B. This wave is the amplitude of E. So you need to remember how to go from E to B. That's what this question is testing. Nope. K is the wave number, you just do pi over lambda. It is not actually. All right, give you all 30 more seconds. And 5, 4, 3, 2, 1. So this is a very simple problem if you realize the relationship between these. We just derived this. In fact, I'm going to write it another way just for... remember that C equals E over B. That was in the last slide. So... therefore, B naught equals E naught divided by C. In this problem, the value of E naught is 5. That is the amplitude of E naught. That is the, remember this is amplitude. Make sure you keep in mind as you're working through this, these numbers represent something. This is the amplitude of the electric field, the maximum value it can be. And when you plug this in, we get that the maximum value that the magnetic field can be is 1.67 e to the minus 8. It's much smaller. It's hard to make strong magnetic fields.
Can we assume that those like E naught and B naught
Are always what?
like standard units?
Yeah, great question. Can we always assume they're in standard units? Yes, that's a good assumption, and it's otherwise also used. All right, it'd be better if I had told you, honestly, but okay, already talked about this. So let's do a more involved problem. All right, this one is going to be like the most complicated version, and I probably won't do this. We'll see as we unpack it. But I picked this one because visually it's a good problem to understand how these fields look relationally. All right, so let me read through it and I'll show you what I mean. But I'm not going to ask you one that has an update problem. All right, a plane electromagnetic wave, all these waves are plane waves, meaning they act like an ocean wave. You get a big flat wave that's kind of heading towards you. Everywhere on that wave is kind of, think of an ocean wave. It's big and long. It's this big, long, flat thing heading towards you. That's what these waves are. To show you all a plane wave, because I do want you to understand what a plane wave is, so let's go back to that simulation. Because you're going to hear this phrase plane wave a lot of times, and it won't actually matter too much. Oh, thank you. This is a plane wave. It is still a wave. If I look at it from the 3D view, it's a little bit easier. Now, I don't know why it's got these weird, don't worry about these divots. It shouldn't really have those. If we look at it from the side, that's what I need you to know. It's these waves that kind of move left, right. Yeah, I'm not quite sure why we're getting these weird things, these weird destructive and constructive things, but I think it's because of the walls. Don't worry about it. Look, it's a bunch of ocean waves heading at you. Plane wave. Great. All right. So, a plane wave has a frequency of 600 times 10 to the 12 hertz. It's propagating, meaning it is moving. The word propagating is another way of saying which way it's moving. It's a fancy word we use for waves. In the positive x direction, in vacuum, and has an electric amplitude of 42.42 volts per meter. If the wave is linearly polarized, meaning it just oscillates in one direction. The word polarized is a fancy phrase to say it oscillates in one direction. Such that the electric field oscillates at a 45-degree angle of the y-axis. What are the equations for the components of E and B? I'm going to draw a picture of what this wave's doing before we solve the problem so you can understand, because there's a bunch of weird words in here. So here's a coordinate axis. This is X, this is Y, this is Z. Classic, right? My wave is moving along the x-axis. My wave is moving along the x-axis. My electric field is wiggling 45 degrees above the y-axis. So this is very hard to draw. It is wiggling at this kind of angle and moving this way. The magnetic field will be exactly perpendicular to it. The magnetic field is going to wiggle this way. Gosh, my chances of drawing this well are like non-existent. Yeah, maybe. I'm not proficient with Desmos, so I wouldn't be able to do it. But the idea here is as this wave travels, my electric field wiggles like this. My magnetic field wiggles like this. All right, they're perpendicular to each other. That's the idea here. All right, great. We need to make the equations. Let's look at our general equation for it. My electric field should be something.
Is it always Y? Because of that?
So this is the key here. It's not going to be Y. Actually, in this case, it's X. Thank you. X is the direction of travel. Sine of 2 pi over lambda times X minus plus CT. Great. All you all need to do at first is plug the numbers in where they go. What is the value of E naught? That is very simple. It tells you in the problem. The value of E naught is 42.42. What is the value of lambda? Lambda is not given in the problem. But what is given is frequency. Why is this useful? I'll remind you all the formula sheet because it's one of the most useful things when you're solving this is to have this on hand. If only I had a relationship between frequency and wavelength and a number I have. There it is, V. So remember, this is any velocity, this is true, but I replaced it with C because for light it's always C. V equals F times lambda. What's the velocity of light? C. So C equals F lambda, therefore lambda equals C over F. So therefore lambda equals 3e to the 8 over 600 e to the 12. I'm just going to write this, I'll just plug in my calculator. All right, so I get 5e to the minus 7. It's small. All light has a small wavelength. Okay, that's not true. A lot of light, visible light has a small wavelength. Visible radio waves, we actually said, are like 300 meters. All right, great, but this is really simple. You just put this in here. All right, great. There's my equation for my electric field. With a caveat, I need to break this into components. It sounds worse than it is.
Why?
This electric field in my picture, it does not point in the z direction. It does not point in the y direction. It points in between the two. This is very simple. How do I break a vector that's a 45-degree angle into its x and y? It's cosine and sine. It's super easy. So if you all want the y component, here are my two components on my picture. If you all want the y, or let's do the z component. That's going to be the thing we just wrote.
Is the original the X component?
The original wasn't any component. It was the net field.
But it already was at 45 angle.
I haven't included that yet. I haven't accounted for that yet. Great, so there's the E field in the z direction. The E field in the, what was the other one? The y direction is going to be the exact same thing, but with a cosine. Times x minus 3e8 times t times cosine of 45. Fun fact, cosine of 45, sine of 45, they're the exact same number, so, you know. All right, I did the electric field. The magnetic field is really easy, y'all. It's the exact same equation, but just take this first number and divide it by 3e8. So I'm not actually going to write that one out for the sake of time, but I will just remind you all. I'll put it up here and I'll put a little star next to it. C equals E over B. Therefore, B equals E over C. So the next one is the same thing. There is a minus sign in one of them. We're not going to worry too much about that.
So you do not want an X component? You not the magnetic field on the X axis?
So the magnetic field will also be in the Y and the Z direction.
Why is it only Y?
Yeah, so this is a great question. These fields oscillate in the ZY plane and they travel in the X direction. Now they never actually point in the X direction. These vectors are not, the vectors always point perpendicular to the direction you're going. If you're like, what do I mean by that? If you like looked at these waves, they oscillate up, down, but they're moving right, left. They always oscillate. All right, so this is 3 minutes is fine for this, and next class we'll do energy.
There was a minus in there too, going up, right?
Yeah, I did pick a minus sign because we're going in the positive direction, so I made them both minus.
You always put X in there? So
If you're moving in the X direction. Whatever direction you're moving, these are great questions. Whatever direction you're moving is the thing that you're a function of. I'm going to always make it X to make our life a little simpler. I don't want to get things too crazy. All right, waves. They can constructively and destructively interfere. This is very relevant for measuring things and for just why waves are significant. So this image here, you see a red wave that's flip-flopping. Where's that red wave coming from? That red wave is the green and the blue added together. So what's happening in this bottom graph here is if I could pause this, I can pause it, yay. If I pause this graph at some time, and I look at this spot right here, it's taking the blue vector, and it's adding the green vector. And the red one is the combination of the two. Waves add together. If one of them is down, you subtract it. If one of them is up, you add it. All waves. You never just have one wave out there. There's always a superposition. When you all look at a lake, there's not just one nice wave moving its way along it. It's a bajillion waves all interacting with each other, adding and subtracting and adding and subtracting, and it gets really messy. So it's important to understand that this is what waves do. They add and subtract from each other. When they're up, positive. When they're down, it's negative. And we get these really big peaks, if I can pause it at the right time. When they're really lined up, you get really big peaks because they're both up at the same time and they're both down at the same time. We call that constructive interference. You get a flat line, I did really good there. When they're exactly opposite, when one's up and one's down, they completely cancel out. You're like, what's the use case for this? Noise canceling headphones. The way your noise canceling headphones work is they literally have a microphone and they pick up all outside noise. And how do they cancel that noise? By playing more noise. They take the wave, they take the sound wave and they exactly flip it. And they play that sound in your headset. And that sound cancels the outside noise and you get effectively that. The better they are, the better they are. So, yeah, that's one example of that. Have a good one, y'all. We'll do energy next time and then Snell's Law. See how much this I can get through. Yeah, I got lucky.